Section 10.1, estimating a difference between two proportions. Back in Chapter 8, we were introduced to confidence intervals, and we started out by calculating confidence intervals for one proportion problems, and it was given by this equation here. We had our point estimate, which is the p-hat, the results of the sample. We'd follow that up by adding and subtracting the margin of error, which is this whole portion of the equation there. Right, the z-score comes from the confidence level. So for example, 95% confidence level would have a z-score of 1.96. And then our standard error is radical p-hat, q-hat, which they're going to write as 1 minus p-hat over n. So in this section, we're doing the same thing, except instead of having one sample, we're going to have two different samples. So we're talking about estimating or creating a confidence interval for the difference between two proportions from two different populations. For example, we might want to estimate the difference in the proportion of all adults and the proportion of all teens who use Facebook. Now, the structure of this is going to be really similar to what we've been doing, with the key difference being that there's two different populations that we're going to be drawing samples from. So for example, we'll be drawing a sample from the population of all adults, and then a separate sample from the population of all teens. And we'll have two different test statistics, two different p-hats. We have p-hat 1 and p-hat 2. We might want to call that p-hat A for adults and p-hat T for teens. The first thing we're going to talk about is what the sampling distribution for p-hat 1 minus p-hat 2 will look like. What we mean by that is if we were to take two samples and find the difference and then repeat that process over and over again and make a distribution of those differences, we're going to get something that's approximately normal, which is what we want, obviously, as long as the condition is met. And the condition is that we have enough successes and failures for each sample. So n times p and n times q for sample 1. And then the same thing for sample 2 are all at least 10. The mean or the center of the sampling distribution is going to be whatever the difference in those two sample statistics are. And then the standard deviation changes a bit. So rather than radical PQ over n, we have a radical PQ over n for each sample. We add those together and then square root it. When it comes to the conditions for this type of test, they're the same as always, randomization and large counts, with an added note that we have to check these conditions for both samples. As for why we're checking these conditions, to start, we check the randomization condition just to make sure we can generalize our results to an entire population. We check the large counts condition to make sure that our sampling distribution is approximately normal. When those conditions are met, we're going to create what's called a 2 proportion z interval, or a confidence interval for the difference in two proportions. And it's going to follow the same format that we did back in Chapter 8 when we initially were introduced to confidence intervals. So we'll start off with our point estimate. That had been just the p-hat, but now it's going to be the difference between our two p-hats, since we'll have two of them. And we're going to add and subtract the margin of error, which had been a z-score times radical PQ over n, z-score times that standard error. Right, but that standard error is going to change because now we have two different samples. So we have two fractions with PQ over n, one with each sample. And since we don't know the actual P and actual Q, these have hats on them because they are sample statistics and not population parameters. When we put those all together, we get this equation here, which starts with the point estimate for the difference in those two proportions, followed up by adding and subtracting the z-score. That's going to come from whatever confidence level we have. We will just look that up in our yellow table. And then that's multiplied by that standard error. This is called a 2-sample z interval for a difference between two proportions. It can also be called a 2-proportion z interval, or a confidence interval for the difference between two proportions. So a full problem is going to look like this. We have a random sample of 1,502 adults. They're asked about whether or not they use Facebook. And then we have a second sample of 743 US teens. Note that these samples are not the same size. They don't have to be the same size. Here we have our two p-hats. This is for the adults. This one is for the teens. And these are estimate our population parameters. So we're going to say P1 is for the adults, P2 is for the teens. For these problems, when we define parameters, we'll be defining two different parameters. So the first thing we'll do is check our conditions. It notes that these samples were random. When we write this, we're writing about both samples separately, okay, and we're not putting them together. When we check the large enough, or as I call it, the success-fail condition, we do n times p and n times q for both samples. So here it is for the adults. We can see both of those are bigger than 10. And then here it is again for the teens. And again, we have values larger than 10. On the quiz, this is going to be broken into parts, but here we're just going to do it all at once. So here's the equation for a 2 proportion z interval. We're going to plug in all those values there. So the p hat 1, the proportion of adults, it was given to us in the problem, is 0.69. The proportion of teens that used Facebook is 0.51. So that difference of 18% is the point estimate. It's a 95% confidence interval, and we're going to look this up in the table. Remember, when we look it up in the table, that 95% gets cut out of the middle of this curve. So we're going to look up the left tail, just this part, which is always half of whatever's left over. So there's 5% left over. That's going to get split equally, 2.5% on the left, the other 2.5% over here. So you'd look up 0.025 in the table to get that z-score. Our standard error, this is for the adults. So we have 0.69, and then it's q hat, which would be 1 minus 0.69 or 0.31 over that sample size for adults, and then the same thing for the teens. Point estimate, adding and subtracting our margin of error is that whole string of calculations after that plus minus sign, and we get our interval from 0.137 to 0.223. Based on this interval, is there convincing evidence that a greater proportion of adults than teens use Facebook? Yes, there is, and that's because all of these values are positive. We're doing adults up here minus teens, and since we're getting positive values, it means adults is bigger or is a higher proportion than teens. Now, in the previous slide, I skipped over the conclusion where we write that sentence saying we are 95% confident that ... So here's how we would do that. We are 95% confident that the interval from 0.137 to 0.223 captures the true difference in the proportion of all US adults and teens who use Facebook. That's the first way we can write it, right? The second way is we're going to look at the order in which we subtracted these when we made our confidence interval, and we had done adults minus teens. Okay, so this is telling us the proportion of adults in relation to the proportion of teens. Since these are both positive, it means adults are using Facebook at a higher proportion. So we could also write it like this. The interval suggests that that adults using Facebook is between 13.7 and 22.3 percentage points higher than teen Facebook use. When we started this problem, there was nothing that stated we had to do adults minus teens. It would be fine if we reversed it and did teens minus adults, and the only thing that would change here is the order. So instead of 0.137 to 0.223, it's going to flip 0.223 to 0.137, and they're both going to be negative, because if we think about this, adults is the higher proportion, teens is the lower proportion. So in this case, we're going to be taking a smaller number, subtracting a bigger number, and we get negative values there. Both of these are correct. It just the only difference in our solution would be how we interpret it. We would say that the proportion of teens using Facebook is between 22.3% and 13.7% lower than the proportion of adults, and that's because our two values in our interval are negative. In this second example, we have some approval polls for President Trump. According to a Gallup poll of 1,525 randomly selected U.S. adults in 2017, January 2017, 686 approved of President Trump's job performance. They took a different sample of 1,526 in October of 2019 and found that 595 approved. We're going to construct and interpret a 90% confidence interval for the change in Trump's approval rating among all U.S. adults from January 2017 to October 2019. So to begin, we're going to define our parameters. The first parameter we'll call it P19, and that's going to be the true proportion of all U.S. adults who approved of President Trump's job performance in 2019, October of 2019. And then P17 is the same, but for January 2017. Next up, we're going to state which inference method we're using. So far, we've learned about one proportion z-tests, one sample t-tests, one proportion z-intervals, and one sample t-intervals. This one is called a two-sample z-interval for the difference in these two proportions. We also can just call it a two-proportion z-interval. We'll check our conditions. We have separate random samples in 2017 and 2019. And when we check the success-fail, here it is for the 2017 sample, and again for 2019, and we can see that all of these values are at least 10. We're going to go ahead and calculate everything, starting with the sample statistics from those two samples. So here it is from the 2019 sample, we get 0.39, and then from 2017 we get 0.45. We'll plug all of these into the equation here. So here's our point estimate. We're doing 2019 first, and then subtracting the 2017 sample. Add and subtract the critical z-score for a 90% confidence interval. So remember that 90% gets cut out of the middle. The leftover 10% gets split in half, where 5% is on the left, 5% is on the right. So we'll look up 0.05 in the table, that yellow table, and we see it's right in between 1.64 and 1.65, so we get 1.645. The standard error, PQ over N for the 2019 sample and 2017 sample. Add those together, square root it. Our point estimate for the difference in those two proportions is negative 0.06. That's just the result of this subtraction right there. And then our margin of error is 0.029. So we end up with an interval from negative 0.089 to negative 0.031. Comes to interpreting the interval, just remember that it's about the difference or the change in the proportions. So we would write that we are 90% confident that the interval from negative 0.089 to negative 0.031 captures the change in the proportion of all U.S. adults who approved of President Trump's job performance from January 2017 to October 2019. We can also write it with a bit more context in it and say that we are 90% confident that President Trump's approval rating decreased. It's decreasing because these two values up here are negative by between 3.1 and 8.9 percentage points between January 2017 and October 2019. The wording on this is a bit important. We're saying it decreased by between 3.1 and 8.9 percentage points. We're not saying it decreased by 3.1 to 8.9%. That would be different mathematically. A decrease from 45 to 39% is a decrease of 6 percentage points. But if we were to divide that by the initial 45%, that would be a 13% decrease to go from 45% to 39%. So we're not talking about a percent decrease, we're talking about a decrease in percentage points. Also, when we look at this interval, if we note that it does not include 0, so it went from negative 0.031 to negative 0.089, 0 is outside of that interval. 0 would indicate that these two proportions are the same. All right, and since 0 is outside that interval, we have convincing evidence that there has been a decrease in President Trump's approval rating over that period of time.